At exactly 5:03 p.m. on a quiet Sunday evening, the ground beneath northeastern Japan began to shift. For those standing in Morioka, the capital of Iwate Prefecture, the first sensation was subtle, a low rumble that seemed to rise from somewhere impossibly deep. Then the shaking began. Not the violent tearing motion that throws people to the ground, but a persistent rolling that made buildings sway and sent loose objects skittering across floors. On the Japan Meteorological Agency's instruments, the earthquake registered as a magnitude 6.9, later revised from an initial 6.7 reading. The epicenter lay 10 kilometers beneath the Pacific Ocean floor, 78 miles east of the coastal town of Yamada, in waters that have claimed thousands of lives before. Within seconds, a cascade of automated systems sprang to life across the region. Seismometers detected the earthquake's primary waves, the fast-moving but relatively harmless P waves that race ahead of the destructive secondary waves. The Japan Meteorological Agency's computers analyzed the data from over 4,200 seismic stations installed throughout the country, calculated the earthquake's magnitude and location, and broadcast warnings to millions of mobile phones, television screens, and radio receivers. The distinctive two-tone chime echoed through homes and streets, followed by the calm but urgent automated voice. "This is an earthquake early warning. Please prepare for powerful tremors." For the people of Iwate Prefecture, these warnings carry a weight that goes beyond mere information. They carry memory. The northeastern coast of Japan sits atop one of the most geologically volatile zones on Earth. Here, in a narrow belt of ocean and land, 4 massive tectonic plates converge in a slow-motion collision that has shaped the archipelago for millions of years. The Pacific Plate, a vast expanse of oceanic crust stretching halfway across the planet, grinds westward at roughly 8 to 9 centimeters per year. As it meets the continental plates beneath Japan, the North American plate to the north and the Eurasian plate to the south, the denser oceanic crust is forced downward in a process called subduction. This creates the Japan Trench, a deep underwater canyon that plunges more than 8,000 meters below the surface. Meanwhile, from the south, the Philippine Sea Plate pushes northward, adding another layer of complexity to this tectonic puzzle. The result is a seismic pressure cooker. As the Pacific Plate descends into the mantle, friction builds along the plate boundary. Water from the subducting oceanic crust is forced into the hot mantle rock above, lowering its melting point and generating magma that rises to form Japan's volcanic arc. But it's the locked boundary between the plates, the place where 2 massive slabs of the Earth's crust press against each other with unimaginable force, that poses the greatest danger. When that boundary finally ruptures, the overlying plate snaps upward, displacing billions of tons of seawater and sending earthquake waves radiating outward at thousands of kilometers per hour. This is the same mechanism that has produced some of history's most devastating disasters, and it's why Japan experiences roughly 90% of the world's seismic activity within the Pacific Ring of Fire occurs in this horseshoe-shaped belt of volcanic and seismic activity that encircles the Pacific Ocean. On March 11, 2011, at 2:46 p.m. local time, a magnitude 9.0 earthquake struck off the coast of northeastern Japan. It was the most powerful earthquake ever recorded in Japan and the 4th most powerful earthquake in global history since modern record-keeping began. The rupture zone extended 450 kilometers north to south and 150 kilometers east to west. The Pacific Plate, which had been slowly advancing beneath the Eurasian Plate for centuries, suddenly slipped upward by as much as 50 meters in some locations. The overlying seabed was thrust upward by 10 to 20 meters, displacing an enormous volume of water and generating a tsunami that would reach heights of 40 meters in some coastal areas. The earthquake shook for 6 minutes, an eternity in seismic terms, giving the energy time to travel across the entire country. Buildings swayed in Tokyo 373 kilometers from the epicenter. In Miyagi Prefecture, directly above the rupture zone, the ground acceleration reached 2.99 g, nearly 3 times the force of gravity. The official death toll from the earthquake and tsunami reached 18,500 people, with thousands more injured and hundreds of thousands displaced from their homes. Entire coastal communities were erased. The cities of Rikuzen Takata, Minami Soma, Kesennuma and Ishinomaki were devastated. In some areas, the tsunami penetrated up to 10 kilometers inland, sweeping away homes, schools, hospitals, and thousands of lives. But the disaster didn't end with the shaking and the waves. 50 minutes after the earthquake, tsunami waves between 13 and 14 meters high struck the Fukushima Daiichi nuclear power plant, overtopping the facility's 10-meter seawall and flooding the lower levels where emergency diesel generators were housed. With both external power and backup power lost, the cooling systems for reactors 1, 2, and 3 failed. Over the next 3 days, all 3 reactor cores largely melted down. Hydrogen gas generated by the reaction between superheated fuel rods and steam accumulated in the upper reactor buildings and exploded, blowing off the roofs and releasing radioactive materials into the environment. The Fukushima disaster was rated a Level 7 event on the International Nuclear and Radiological Event Scale, the same severity as Chernobyl. It forced the evacuation of over 150,000 people and created contamination zones that remain partially off limits more than a decade later. The economic cost of the 2011 disaster exceeded $220 billion, making it the costliest natural disaster in human history.
The seismic data from the November 9, 2025 earthquake arrived at the Japan Meteorological Agency in milliseconds. Magnitude 6.9 at a depth of 10 kilometers, epicenter off the Sonariku coast of Iwate Prefecture. The agency's computers compared this event to their extensive database of historical earthquakes. The depth was shallow enough to generate a tsunami. The magnitude was significant, and the location, this was the critical factor. The earthquake had occurred in the same tectonic zone that ruptured in 2011, along the subduction interface where the Pacific plate dives beneath the continental crust. Within 3 minutes of the initial shock, the agency issued a tsunami advisory for Iwate Prefecture, warning that waves up to 1 meter high could reach the coast. The intensity of the shaking itself was measured at 4 on Japan's unique Shindo scale, which ranges from 0 to 7 and measures the strength of ground motion experienced at specific locations rather than the earthquake's total energy release. Shindo 4 indicates strong shaking that most people will notice, capable of swaying hanging objects and rattling dishes, but typically not causing significant structural damage to modern buildings. Yet what concerned seismologists wasn't the initial magnitude 6.9 quake, it was what followed. Over the next few hours, the region was struck by 11 aftershocks, including one measuring magnitude 6.3. This pattern of continued seismic activity indicated that stress was still being released along the plate boundary, that the rocks deep beneath the ocean floor were still adjusting to the initial rupture. At a hastily convened press conference, a Japan Meteorological Agency official delivered a warning that residents of the region know all too well. Earthquakes of similar or even stronger intensity could occur in the next few days, possibly for up to a week. The aftershock sequence suggested that this wasn't an isolated event, but part of an ongoing adjustment of tectonic stress in the region. The tsunami advisory triggered an immediate and coordinated response across Iwate Prefecture. More than 6,000 people evacuated from coastal areas, moving to higher ground or designated evacuation centers. The evacuation was swift, orderly, and comprehensive, a stark contrast to the chaos of some past disasters. This efficiency wasn't accidental. It was the product of painful lessons learned in 2011 and billions of yen invested in disaster preparedness infrastructure. The J-Alert system, Japan's satellite-based early warning network, broadcast alerts within seconds of the earthquake detection. Sirens wailed from loudspeakers positioned throughout coastal communities. Text messages arrived on millions of mobile phones, many of them triggering distinctive alarm tones even on devices set to silent. Television broadcasts were interrupted by red warning screens showing the earthquake's location and affected prefectures highlighted in yellow on maps of Japan. The warnings weren't just in Japanese. They were broadcast in 5 languages: Japanese, English, Mandarin, Korean, Vietnamese, and Portuguese, ensuring that foreign residents and visitors could understand the danger and take appropriate action. These warnings reached people in their homes, in their cars, at work, in restaurants and shops. Within the 1 seg digital television standard, warnings automatically turned on radios and televisions that had been in standby mode, ensuring that even sleeping households would be alerted. For many residents, especially older survivors of the 2011 tsunami, the warnings triggered immediate action born of traumatic memory. They didn't wait for the ground to stop shaking. They didn't pause to gather belongings. They moved. Prime Minister Sanae Takaichi posted on social media within minutes, urging people to evacuate from the coast immediately and warning that later tsunami waves could be larger than the first arrivals. Local officials activated evacuation protocols that had been drilled countless times. Designated evacuation routes marked with blue signs showing stylized waves and arrows pointing to higher ground guided people away from the shore. In some communities, automated drones took to the air, broadcasting evacuation instructions in multiple languages through onboard speakers. At 5:52 p.m., 49 minutes after the earthquake, the first tsunami wave arrived at Kuji Port in northern Iwate. The wave measured 20 centimeters, less than 8 inches. At 6:25 p.m., another 20-centimeter wave reached Ofanato Port, about 100 kilometers to the south. To someone unfamiliar with tsunami dynamics, these might seem like trivial events, barely more than large ripples. But seismologists and emergency responders knew better. Even small tsunami waves can carry immense destructive power, and more importantly, they serve as harbingers. Tsunamis typically arrive in multiple waves, and the first wave is not always the largest. The water that generates a tsunami is set in motion by vertical displacement of the seafloor, creating a series of long-period waves that can travel across entire ocean basins at speeds exceeding 800 kilometers per hour in deep water. As these waves approach the coast and enter shallow water, they slow down, compress, and pile up, increasing dramatically in height. The 20-centimeter waves observed at Japanese ports represented the leading edge of this disturbance, the first pulses of displaced water reaching the shore. The tsunami advisory remained in effect for 3 hours, during which coastal areas stayed under evacuation orders. Emergency personnel monitored tide gauges at ports throughout the region, watching for any indication that larger waves might follow. Scientists at the Japan Meteorological Agency Tsunami Warning Center analyzed the earthquake's focal mechanism, the precise way the rocks moved during the rupture, to refine their predictions of tsunami behavior. Throughout this period, residents waited in evacuation centers, many of them carrying go bags packed with emergency supplies: water, non-perishable food, flashlights, first aid kits, copies of important documents, and medications. These preparations, too, were the legacy of 2011. Within minutes of the earthquake, automated safety systems across the region sprang into action. The Tohoku Shinkansen, the high-speed bullet train line that connects Tokyo with northeastern Japan, lost power between Sendai and Sin-Aomori stations. The trains, which normally travel at speeds up to 320 kilometers per hour, executed emergency braking procedures. The earthquake early warning system had detected the P waves and sent shutdown commands to the train control systems before the stronger S waves arrived, giving the trains crucial seconds to begin slowing down. This technology, developed after 2 previous derailments in the 2004 Chuetsi earthquake and the 2011 Tohoku earthquake, potentially saved hundreds of lives. Within 2 hours after thorough track inspections confirmed no damage, train service resumed. At the Onagawa nuclear power plant in neighboring Miyagi Prefecture, automated systems detected the earthquake and initiated safety protocols. The plant's operators immediately checked all systems for abnormalities. They found none. The plant's seawall, built to a height of 14 meters following the Fukushima disaster, had not been tested by tsunami waves this time, but it stood ready. At Tohoku Electric Power Company's other facilities throughout the region, emergency response teams activated, ready to restore power to any affected areas. A brief power outage affected an unspecified area of Iwate Prefecture, but backup systems and rapid response minimized the disruption. The infrastructure response demonstrated something crucial. Japan's investment in earthquake-resistant design and automated safety systems was working. Buildings swayed but didn't collapse. Trains stopped safely. Nuclear facilities responded appropriately. The systems designed to protect lives were functioning as intended. The seismic monitoring systems that protect northeastern Japan today bear little resemblance to those that existed before 2011. More than 4,200 seismometers blanket the country, many of them placed in schools and other public buildings. These instruments feed data in real time to the Japan Meteorological Agency's computers, which can detect earthquakes and calculate their magnitude, depth, and location within seconds. The earthquake early warning system, launched in 2007, has been continuously refined. It works by exploiting the difference in speed between P waves, which travel at about 6 kilometers per second through the Earth's crust, and S waves, which travel at about 3.5 kilometers per second. Because S waves carry most of an earthquake's destructive energy, the seconds or minutes of warning provided by P wave detection can be life-saving. In densely populated areas close to earthquake epicenters, the warning time might only be seconds, but seconds matter. They allow people to drop, cover, and hold on, to get under sturdy furniture, away from windows, into doorways. For critical infrastructure, the warnings trigger automatic responses. Trains brake, assembly lines stop, gas lines shut off, elevators move to the nearest floor and open their doors. Japan's tsunami warning system has also evolved dramatically. The underestimation of tsunami height in 2011, initial predictions of 3-meter waves that eventually reached over 10 meters in some locations, led to fatal complacency. The system now uses moment magnitude calculations, which take longer to compute but provide more accurate estimates of earthquake size and tsunami potential. Coastal communities have installed tide gauges and GPS buoys that can detect tsunami waves in real time, providing ground truth to supplement computer models. Perhaps most importantly, Japan has invested heavily in disaster education and cultural preparedness. September 1st is Disaster Prevention Day, commemorating the 1923 Great Kanto earthquake and serving as an annual reminder to review evacuation plans and emergency supplies. Schools conduct regular earthquake and tsunami drills. Coastal communities practice evacuations. The message is clear and consistent. When the earth shakes near the coast, you move to higher ground immediately, without waiting for official warnings or stopping to collect belongings.
The events of November 9th, 2025 demonstrate both the progress Japan has made and the persistent vulnerability of living in one of Earth's most seismically active regions. The rapid response, efficient evacuation, and infrastructure resilience all reflected lessons learned from past disasters. No lives were lost. No significant damage occurred. The systems worked. But seismologists understand that this was, in geological terms, a relatively modest event. A magnitude 6.9 earthquake releases about 1/30th the energy of the magnitude 9.0 earthquake in 2011. The 20-centimeter tsunami waves that reached Japanese ports were tiny compared to the 40-meter waves that devastated coastal communities 14 years ago. The tectonic forces that generated the 2011 disaster haven't diminished. The Pacific Plate continues its relentless westward march, descending beneath Japan at nearly 9 centimeters per year. That's roughly the rate at which human fingernails grow, but across the vast area of plate contact, it represents an accumulation of enormous strain energy. Much of that energy was released in 2011, but the plate boundary spans hundreds of kilometers, and different segments rupture at different times. The southern portion of the Japan Trench, off Fukushima Prefecture, ruptured catastrophically in 2011. The northern portion, off Hokkaido, last experienced a major rupture in 1893. The Kuril Trench, extending northeast from Japan toward Russia, has its own history of massive earthquakes and tsunamis. In September 2025, the Japanese government designated 108 cities, towns, and villages in 7 prefectures as tsunami-threatened areas, requiring enhanced protection measures. These designations came with funding for evacuation infrastructure, tsunami evacuation towers where vertical escape is possible, elevated evacuation roads, emergency supply caches on high ground. The government has set a goal of reducing potential fatalities from a massive earthquake along the Kuril and Japan trenches by 80% over the next decade. Living in Japan means living with the certainty of earthquakes and the possibility of catastrophic tsunamis. It means constructing every building to withstand violent shaking, designing every bridge to flex rather than break, training every schoolchild to recognize the warning signs of a tsunami and know the route to higher ground. It means accepting that the ground beneath your feet is never truly stable, that the ocean at the end of your street could rise up in a matter of minutes and sweep everything away. This isn't a comfortable truth, but it's one that Japanese society has internalized. The culture of preparedness that has developed, the go bags by the door, the emergency supplies in every home, the automatic responses drilled until they become instinct, reflects a profound acceptance of geological reality. The Earth is not a passive stage upon which human activity unfolds. It's a dynamic, powerful system of which we are merely temporary residents. The tectonic processes that built Japan, that raised its mountains and carved its valleys and created its hot springs and fertile volcanic soils, continue to operate on timescales that dwarf human lifetimes.
A century is nothing to a tectonic plate. A millennium is a blink. The rocks beneath our feet carry memories measured in millions of years, records of past collisions and ruptures that predate our species. In northeastern Japan, those rocks remember 2011. They remember 1896, when a tsunami killed 27,000 people. They remember 869, when the Jogan earthquake and tsunami devastated vast areas of what is now Miyagi and Fukushima prefectures. And they're building toward future ruptures that will occur whether we're ready or not. The magnitude 6.9 earthquake on November 9, 2025, and the modest tsunami that followed serve as reminders of what this region faces. They demonstrate the effectiveness of Japan's disaster preparedness systems, but they also highlight an uncomfortable truth. We can prepare, we can warn, we can evacuate and build and engineer and drill, but we cannot prevent. The plates will slip, the rocks will rupture, the earth will shake, and the ocean will rise, and all we can do is survive. Yet there's something profound in that survival, something that speaks to human resilience and adaptability. Japan hasn't abandoned its coasts despite the danger. Communities devastated in 2011 are rebuilding, albeit higher and farther from shore. Fishermen still put to sea. Children still play on beaches. Life continues in the shadow of tectonic forces because humanity has learned, slowly, painfully, at enormous cost, how to coexist with geological reality. The warning systems that saved lives on November 9th represent more than just technological achievement. They represent collective memory, societal learning, a commitment to protecting future generations from hazards that cannot be eliminated but can be mitigated. Every seismometer installed, every evacuation route marked, every drill conducted, every warning broadcast is an act of defiance against catastrophe. Not a denial of danger, but a recognition that while we cannot control the Earth, we can control our response to it. The Pacific Plate will continue its westward migration. Stress will continue to build along the plate boundaries. Future earthquakes are not just possible, but certain. Some of them will be massive, magnitude 8 or 9 events that rupture hundreds of kilometers of the plate interface and generate tsunamis capable of crossing entire ocean basins. These events will happen. The only questions are when, exactly where, and how ready we'll be when they do. Japan's experience offers crucial lessons for other regions facing similar hazards. The Pacific Northwest of North America sits above the Cascadia subduction zone, where the Juan de Fuca plate dives beneath the North American plate. That boundary last ruptured in 1700, producing a magnitude 9 earthquake and tsunami. It will rupture again. Indonesia, Chile, New Zealand, and other nations around the Ring of Fire face similar threats. The technology, the warning systems, the culture of preparedness that Japan has developed aren't luxuries or overreactions. They're necessities for survival in geologically active regions. If the November 9th earthquake accomplished anything beyond the immediate evacuation of 6,000 people and the safe halting of high-speed trains, it was this. It reminded us that the Earth is always moving beneath our feet, always adjusting, always releasing the enormous energies generated by plate tectonics. It reminded us that we live as guests on a dynamic planet, that the stability we experience day to day is an illusion maintained only by the slowness of geological processes relative to human timescales. And it reminded us that our best defense against these unstoppable forces isn't walls or engineering alone, it's knowledge, preparation, rapid response, and the collective determination to protect each other when the ground begins to shake and the ocean begins to rise. If you found this account revealing, consider subscribing to see how Earth continues to reshape itself beneath our cities and along our coasts. The plates are still moving, the next rupture is building, and the story of life on an active planet is far from finished.